Okay, so I'm looking at this, and I think when I wrote this yesterday, that, this diagonal cross check here seems wrong. So the layer and the exponent here, and we're getting these numbers. So this 616 here, right? It's coming from here. And then this 656E is coming from here in the test data. And this 6F70 is coming from here. Now the only problem with that is this is our output table. So we're trying to work backwards from the outputs and derive the inputs. And so for the first test, this is the data for the first test right here. And this diagonal here says it's looking at the layer and the tile exponent. Well, the tile exponent is all the different tile exponents are encoded into every single 16-bit value here. So this 16-bit value here encodes different tile values for different tile exponents. Same thing with this bit value here. It encodes 8 different tile exponents for 8 different tile values. This here also encodes 8 different tile exponents for 8 different tile values. So this tile exponent thing here, with this 0, 1, and 2, I get the idea where I was thinking that, you know, this axis here was the layer axis, and then going down was the exponent axis, but that's absolutely not true. You can even see from the numbering that this goes over, it goes over 7, right? So that can't be the case. So this diagonal check is complete crap. So I'm doing a sanity check to make sure that my code's right, but my sanity check is wrong. So the original sanity check was written at this time, and then we want to make a note that the sanity check was wrong, right? So we want to just say so that's great. So, you know, you write test code to make sure that your other code is right, but then your test code ends up being wrong, and it's just, it's like a whack-a-mole almost. So 102, so it's video number 102, and the time of this recording is 0 hours, 31 minutes, and let's just call that 32 seconds, right? So, once again, let's kind of restate for the camera that this entire sanity check section is wrong, right? So this thing that says big lit, well, first of all, that is also wrong, right? Because look at this. It says 1 is big lit, but then here it says 1 is big lit, so that's wrong as well. This needs to be a 2, right? Because we need to look at, this is for the big endian, right? This is big endian. And right here is the little endian, right? So it's looking at, here's our big endian table, and then here's our little endian table. So that's wrong. So, yeah, we just got a lot of stupid mistakes here. But, okay, besides that big lit thing being wrong, the other thing is these values here, right? So this value, and this value from the big endian table, there are these values, these diagonal values here, right? So looking at layer 1, layer 2, and layer 3, or, sorry, these first layer, second layer, and third layer. So, first layer, second layer, and third layer over here. And then we're going diagonal on the exponents, so we think we go diagonal, but when we go down on the axis here, when we go down the screen, we're not changing the tile exponent because this value here encodes 8 different tile exponent tile values. This encodes 8 different tile exponent tile values, and this value here encodes 8 different tile exponent tile values. So that diagonal is completely wrong because this is all the data for the first test. And I know what the sanity check was for. It was for checking the first block of values, right? So hard coding just the first test here and seeing if we were iterating through the data correctly. And that's great and all, but it would make more sense if we actually were, I don't know, checking this correctly. So if we look at this, what we're trying to detect is that we're iterating through these data sets correctly. And that's fine. but tile exponent, it really shouldn't be tile exponent, right? So we're trying to just do a little quick diagonal check for our sanity. And if that's what we want to do, then we're not looking at tile exponent here. We're actually looking at the test index. So this is the test number 0, test number 1, test number 2. So up here, we have the exponent, the layer, and the test index is actually this I1 right here, right? This test index here. So we really want to take the test index, and right, we're doing some multiplication with the test index, but the idea is to just hard-code it and say, you know, for these combinations of values, so we're actually looking at the layer and the test index. Right? So that's actually what we're looking at. And maybe, if we're lucky, this sanity check will no longer fail. Now let's just put this sanity check failed. I'm just going to say sanity check failed. We're going to keep on looking at the sanity check, which now it's kind of worrying me because I wrote that sanity check 2 days ago, and the sanity check's failing, and we can see that the sanity check logic was wrong. So now we're going to try to correct some code that was, you know, not correct and try to get it working. And yeah, extracted table wrong, big endian. Okay, so also, if you're new to this stream, I'm going to just throw in my technical demos into the chat so that you can take a look at those. I'm working on a fractal auto-tiling engine. Today is not going to be a fun day. I'm just going to say that right out there, right now. Because it's just a lot of unit testing for some just crazy code, and it's not going to be fun, but it's just stuff that needs to be done. So unfortunately, that's where we are. Okay, so we see this little error message. It looks like maybe, if we're lucky, we got past the sanity check. So 8,562. So let's see where this message is coming from. Hopefully, okay, so it's a little bit further. So that's nice. And so we have a little timestamp. It says, loop through the first generated block of test input values to make sure we are generating them correctly, right? So the idea is, right here, we can see these two blocks of data. So this block and this block, they are going to be derived from these tables. So these first three values, this value here is going to generate all of this binary. This value right here is going to generate all of this binary, and these are 2-bit binary values. This value here is going to generate this binary here. And then down in the little endian section, we have the same exact data, but in little endian format. And this value here is going to generate this data here. This value here is going to generate all of this data, and then this value is going to generate all of this data. And so this is the first test case when we go through the big endian data. And this is the second test case. So we're working backwards. So right here, this is actually our answer key. So this is the answer key for the first test, answer key for the second test, answer key for the first test, answer key for the second test. But we run the tests twice, one with a whole bunch of big endian data, and then another time for all of the little endian data. This is the second time we've written this test code, but I thought that we could get more values if we start off with 16-bit binary values, just because C does not have a binary literal type, so it's very hard to manually transcribe the binary for each one of these. So I thought, well, why not just start off with an unsigned 16-bit and then work backwards to get the starting values. So this is the answer key for the first test, and this is the inputs for the first test, if that makes sense. So for the very first test, we hard-coded this answer key here because we were concerned that we may have extracted the data in the wrong way, right? We're adding a lot of extra complexity to the test data, and how we're deriving that test data. So we just wanted to check the first test with some hard-coded information to check our math to make absolutely sure we're doing everything correctly. And it turns out that something we're doing is absolutely wrong. So we have to figure out what that is. So the first thing is we got 24 values here, 24 values here. Where are we checking these, right? So it looks like here we're checking them. So if it's the big endian test. So this is big endian. So we're going to do big endian first. And then over here, we're going to do the little endian test. So for both the big endian data and the little endian data, we want to check the first set of values for the first test. So extracted table wrong big end and extracted table wrong little end. And I'm pretty sure this is the one we got, but I'm not sure because I'm kind of losing my place here. But we wrote a little utility to kind of help us check things. So we have this, this is the check value, and this is the actual input table. So this thing that says tab UTC in is actually assigned to either here, or it is assigned to here, depending on if this is the big endian or little endian test. So you can see it highlighted right here, right? So, or actually, right, and then we have the big endian and little endian. So this is our little check test data. This is our checking data here, and this is our checking data here. And this right here and this right here is pointing to either this block of data or this block of data. So what I would like to do is use our newfangled utility that we wrote yesterday to check for bitpacking mistakes and throw it in here. So I think where we want to put it is probably right before we throw an error. Let's do like a printf instead. We're going to just change the error message to make it a little bit shorter because we're running out of column space here. But we're going to do a printf instead of crash, because the next thing we're going to do is we're going to manually compare these values with a little utility that's going to look for patterns in the bits to see what kind of mistake we might have made. So let's it also might be nice to have that utility tell us how many of the 2-bit values are off, right? Because we're trying to pack 2-bit values, so there's the potential that in this key here that we got one of the 2-bit values wrong in this hard-coded information. And so you might find that the binary value almost matches, except there's like 2 bits in a certain location that are wrong, and we might want to add that type of pattern checking into the utility. So yeah, we're going to print this. Then we're going to run our assert function. We're going to check with the check data, and then we're going to check with that, and then we're just going to, I don't know what we're going to call this, big in, I don't know. I don't know what the message is going to be called. I'm not too worried about that. So this is a macro for our assert and inspect function. Then over here, we're going to take same deal, except instead of big, it's going to be little. And then we're going to hope that maybe this utility will catch something, right? It will crash the system no matter what, because these two values are different. And it's an assert function with just some diagnostic information in it where it looks at the bits. So we'll give that a run, and hopefully we can derive a little bit more information about what's going on here. And it looks like we actually have to make that macro again. Hold on. So I thought I called it AII, but maybe I guess I did not call it that. So assert something or other. Let's go up to our utilities. Assert and inspect. Oh, it's probably AII. This is what I get for... Okay, yeah. So it's AII for assert and inspect. AII. Okay. So going back down here. Not here. Assert and inspect. AAI. Oh boy. AAI. Assert and inspect. And then we'll just say, you know, AAI. So, and this error message needs to be changed, so this is going to be the little endian, right? So we got the big compared with in, so big compared with in, and then we have a little compared with in, and we see little in here, and AII for the command macro. Okay, let's try that out and just see what happens here. And I'm hoping to see something, but now that I realize that there's the potential that we bitpacked things wrong, extract table wrong. Yeah, so these values are just completely different, right? There's no sign that, yeah, I'm not really seeing anything here. So, now that I realize that I really want to be able to check for values that are bitpacked wrong, where we just like, right, so we are bitpacking all these 2-bit values. There's the potential that maybe we got just one of them wrong, or a few of them wrong. So it might be interesting to know how many of the 2-bit values do not match, right? Because if we find that only one of the 2-bit values does not match, that's kind of a sign to me that we've made a mistake with this hard-coded table here. So we're going to go into the utility we were writing yesterday. We're just going to add some more code to it, I think. So, or do we want to add more code to it, or do we want to? Yeah, we should just add more code to it. So, so in our repo drive in Git, we got kanji coder. And this is the utility we wrote yesterday. Let's open that up and actually make something that is going to tell us about specifically 2-bit values that may have been improperly transcribed. So we have a little bit of checks here. So if the values aren't equal to each other, we do a few things. We check for swapped bits. We check for a pair of 2 bits packed in wrong order. We check for a cluster of 4 bits. And this cluster of 4 bits, what are we doing here? Oh, so we're, so if we packed the clusters of 2 bits in the wrong order, versus if we packed the cluster of 4 bits in the wrong order, versus if we just packed the individual bits in the wrong order, right? We flipped the binary. Or not flipped, because I don't mean like flipping a bit by turning it from 1 to 0. I mean kind of like a rotation of the bit field. So we should do another check somewhere in here. And here's our endianness check. We just want to check to see how many of the values. Let's just make a little section here. Improper So the question is, well, how many of those values need to be a mistake for me to say that I'm pretty sure that it's improper transcription, right? So how many of these, if there are 8 values here, how many of them need to be a mistake? Right? Because they're all different, then we can't really say that there's improper transcription. But if everything but one is incorrect, then we can be pretty sure that there's some type of improper transcription. So I'm thinking it needs to be less than half, right? So if we have, so not 4, but let's say 3, right? Let's say that if 3 are similar, we might want to say that there's a possible improper transcription. Sure. So what we're going to do is we're going to steal this piece of code here, this temp variable. And it looks like what we've been doing is we've been not messing with the first value. But we've been kind of altering the second value. So we just want to loop through everything. So we want to go like for dex equals 0. Dex is less than or equal to, let's do, we really want to do this, 16 divided by 2 minus 1, because we're doing pairs of 2. Okay. And we just want to look at every single bit, right? So we're going to look at U16 1, and we're going to shift it over by dex times 2, and then we're going to mask it, right? We're going to mask it with a 3-bit or a 2-bit mask, right? And we want to compare it with, we just want to say that, you know, if this value right here is not equal to, so we're going to take the same value, or this, we're going to take the second integer that was inputted into this function, we're going to shift it over as well, right? And we're going to mask it. And if they're not equal to each other, we're going to say, let's just use this temporary variable. Number of non... So I'm going to take this and just say, we're just going to increment the number of non-matching 2-bit values. And we'll say that, I'm going to assume that any more than, 3 or... I'm going to hope that when I make mistakes that I've only made, like, maybe 2. Like when I'm looking at this and thinking about how many mistakes I could make when I transcribe this, I'm going to hope that the maximum amount of mistakes I could make is 2, right? Like maybe 1 mistake in this cluster, 1 mistake in this cluster, right? Like, so, 1 out of 4 times I make a mistake. Let's hope for that. And so... yeah, I think 2 is enough to where I'm going to say, or I'm going to have a message. So, if, so, if there's no mistakes, then there's nothing to say about it. But if there's 1 to 2 mistakes, or differences with those 2 bits, then I want to say that I want to have a message about that, right? So I just want to say, like, print f hard-coded 2-bit table, maybe, so just make a note here, you may have made a mistake when you, created the table of 2-bit values to, Bitpack together, possibly, 1 or 2 of them was written down wrong, right? So I'm thinking that, you know, maybe I made a mistake here and I wrote down one of those things wrong, right? So that's just a guess, right? And we might want to say, you know, if U16 temp, if 1 equals U16, or actually no, we can just say printf number of mistakes num mismatched pairs %d \n, and then we can put the U16 temporary variable. Right. Okay, so I like that. I think that's a good comparison if I got that correct, right? We got this bit mask of 2 bits here, and we mask it off. We shift it all the way into the least significant bit position before we compare them, and we see if they're not equal to each other. That looks good to me. If they're not equal to each other, we increase this, and if the number is between 1 and 2 mistakes, then we're going to assume that it's a mistake and it's not just a wildly different integer, right? So let's give that a shot. So let's go over here. So this is our build script is over here. So let's just double click this, see if we made any stupid mistakes, like syntax wise, and it doesn't look like we did. Okay, cool. Now let's do a git bash here so we can use the utility we just compiled. And we need some type of an example value, right? We need an example value, so we're going to have to open up a calculator here, and we're going to have to come up with an example, 2 examples. One example where we have only one sequence of 2 bits wrong, and another example where we have 2 sequences, or 2 clusters wrong. So if we go over here and we kind of bit fiddle here, we got 16 bits here. So, I mean, the easiest thing to do would just be compare 0 with, you know, something like, you know, something where there's just 2 bits set, right? So, if we really wanted to make it easy on us, we could just say compare 0x000, and we could compare that with 0x3, right? Because 3 would be, yeah. So that would be the easy route. And then also we want to do something with 2 more clusters, so we could do this as well. So we could do this. We could do this with 15, which would be 0xf. And we might want something a little bit less naive than that, or something kind of a little bit more interesting, maybe. So why not kind of interlace a whole bunch of 0s and 1s like this, right? And then say, why not compare 0x and then let's change one of these clusters of 2. So how about we change over here? Let's change this one right here. So now this cluster doesn't match, and that's going to be 0x ABAA, right? And then I think maybe it probably means we can do 0x AAA, and then we can probably do, like, for 2 of them not to match, we could probably do a 0x ABAB, right? So if we go over here, we set this, so yeah, ABAB, right? So all of these values should be able to trigger the hard-coded 2-bit table error. So let's take that and see if we can find something, right? So let's do /, let's zoom in here for a second, /basu16.exe, and we're gonna give it all the values just to see that everything is functioning properly. So we're gonna start off with the simplest case. So number of mismatched pairs is 1, and hard-coded 2-bit table error. Okay, awesome. So that is working properly. Let's try F, right? So we're expecting 2 pairs of bits to be off. And yeah, so we got 2 pairs of bits. Okay, cool. Let's try all A's and then 0xABAA, right? And we have 1 pair off there. Okay, let's try that, but do AB, AB. And now we see there's 2 mismatched pairs, right? So, obviously, if we transcribe everything incorrectly and we make 100% mistakes, then we can't really tell if the error was a transcription problem, right? So this is kind of relying on the fact that when we make a mistake, we only make a few mistakes. We don't make, like, everything a mistake, right? So now that we have that, the next thing is, do we have a little crash in here for when it's not equal? I think we do. Oh, actually, before we do that, let's take this and say get status, get commit, or actually get add get commit dash am, and we'll just say now checks for transcription of 2-bit errors. Okay. Oh, we already pushed it, right? No? No, we didn't. Did we? I don't think we did. Okay. So, with that feature, I know we kind of edited this. What we're going to do is we're just going to hackishly kind of take the new case we wrote, and we're just going to shove it in the other code, right? So, improper transcription of 2-bit values. This section here that we just wrote, we're just going to steal this code here and do some horrible code reuse that people are going to, like, cringe at, but that's the way I'm going to do it. I'm going to just look for... I'm going to look for this. I'm going to find... Oh, here's that function here, right? And you have all these different sections. And I'm just going to paste the new kind of check down here. Right, and be done with it, right? Okay, so now that we have that, let's give it a run and see if maybe, just maybe, it catches something. Or maybe it doesn't, but, you know, it was worth a shot, so... I am getting really sick of this unit test code, but... Okay, so let's lazily invoke the unit tests for the new code we were writing and see if maybe... we find something. Extracted table wrong, big endian, mismatched pairs, 1. So there's only 1 mismatch. That kind of tells me that maybe I got lucky here, and maybe the mistake is just in the transcription of the data, because it says 1 mismatched pair. So it's only... So to have only 2 bits in a very specific, you know, 2-bit aligned section in that uint 16, to have those 2 bits that are... Not only is it only 2 bits that are wrong, but they're also aligned to a 2-bit boundary, right? And there's only 1 mistake, so I'm going to take a guess, and I'm going to think that maybe that table of hard-coded data, I made a mistake in it, right? So let's go look at that table of hard-coded data. And we know we are in the big endian data. And... let's see, so DC is 4, big is 0, in is 1. So we have to figure out, well, what do those things mean? So DC, I wish I would, dex check is what that stands for. We're going through the table. Okay, so we're going through the entire table and we're just checking it against itself. Okay. And what about in? What does in stand for here? Well, in is just the value, right? So big and in, we're just checking those values against each other. So we have a 0 versus a 1, is what's happening. And it's happening at the index of 4. Okay. So the index of 4. So let's go look at index 4 here. So 0, 1, 2, 3, and 4. So right here, on this line, so let me highlight this line. On this line here, 0, 1, 2, 3, and 4, right in the middle there, we're getting a, we've hard-coded 0, but the table of data that we have is telling us it should be something else. So if we look at this, if we cross-check this, This is a column right here. This is a column that's derived from this number right here. So what could be nice is if we could, it could be nice actually if we made like a little utility to generate these columns. But for now, we're just going to manually do this, right? So we're going to see if that, maybe we made a mistake doing this. So we're going to take this value, and we're going to, also, when we look at this, we got to make sure that we, right, the tile exponent, we're going from lower tile exponents to higher tile exponents, and that's important because when we start to unpack the bits that are at the most significant bits are going to end up at the bottom of our list. So usually you read a list from top to bottom, but we need to actually go through that list backwards when we're reading through the bits of this. So the first thing I could do is I made a binary printf command, so we could actually try to make use of that utility we wrote. So let's go open up our kanji coder repos folder, and let's go and find that utility. Right, so in the R drive, git and kanji coder. So this binary print utility right here. So let's give this a run. So git bash here, and we're going to take, we're just going to do ./binprin.exe, and then we're going to supply 0x6332, right? And we're going to try to print off the binary there, right? And so now we have we only care about the 16 bits here, so let's take these 16 bits, copy them, and right here, these are the most significant bits, and the way I wrote the code, which maybe I regret doing it this way, but these are this 2-bit value is for the highest tile exponent value, whereas this 2-bit value is for the lowest tile exponent value. So as I take these 2-bit values, I want to draw them down here like this. And I am going to cut and paste so I don't make any mistakes when I manually transcribe, right? So I'm going to do it like this, just to make absolutely sure that I'm not making a mistake, right? And then after I've done this, I know that all of my binary constants start with like a B underscore like that. So what we're gonna say is like maybe, so this list here should match what we've just made, right? And if it doesn't match exactly, then we've made a mistake. So let's look at this. So this looks pretty much like a exact match, right? Well, it doesn't look like we've made any mistakes, right? So here, 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 and here. That all matches, right? So I'm thinking that that we haven't really made a mistake with this. Now, we could check the other values as well, like since we're here, right? Since we're here, we might as well check them all, right? So let's actually take this big block here and just make absolutely sure it's correct, right? So we'll just take this block, and then we'll take the values that are used to generate each one of them. Oop. Alright, so copy this. And so this is for this column, this one is for this column, and this one's for this column, right? And so we already know that the middle column is correct, but we might as well just, while we're here, run it for other values and see if we can find any mistakes, right? So let's take this value for that first column, and let's just painstakingly kind of do this, because maybe when we were looking at those indices, maybe we read those indices wrong and we were off by 1 and we were looking at the wrong column, right? So we might as well kind of tediously kind of check this to see if possibly we made another mistake somewhere else with the transcription, right? And so if we check this and we're absolutely sure it's transcribed properly, then we're going to have to assume that the problem is in how we are auto-deriving, right? We have a loop that we're going over this value in a loop and deriving this block of data, but we hard code it to make we hard code the first block of data to make sure that we're automating the process properly. So anyways, let's see if this is all correct. So first one lights up like that. That looks good. That looks good. That looks good. Yeah, so that looks good. That looks fine. Okay, let's do this last one right here. So let's do this last one, and then after that, I'm going to assume that I'm transcribing my test data properly, and I'm making a mistake when I'm auto unpacking it. So let's take this value here, copy it, paste it down here, and then let's just, right, so this is the third value, and hold on. Did I just... Hold the heck on here. Okay, I'm doing this wrong right now. Because I'm taking... Because the lowest value is going to end up on the bottom right now. I'm doing this process wrong right now. But I'm going to keep on doing it, because if it matches, it means that if this matches this data, that means I did the process wrong for my table. So no, this doesn't match. But I know I did that process wrong. I have everything inverted because I wasn't paying attention. So let's flip that around. This is what I was talking about, everything being backwards. Because the most significant bit is at the bottom of the list. Right? Now if we take that and we compare it to the last thing, that matches, that all matches, that matches. Yeah, so that's fine, that's fine. Okay, so yeah, I think that in terms of the hard-coded blocks of data that I'm using to check my test data, I think that's actually working correctly. I think I've actually hard-coded this correctly, and something about the algorithm I'm using to generate the output blocks of data is wrong. And oh boy, because there's a lot of data here. So we're going to have to we're going to have to look through this, and there's just way too much stuff here. I don't know how I'm going to figure it out. There's just so much formula in here. And no wonder I have a sanity check for this. So yeah. So we generate all the data. So what kind of asserts could we do to check that we're going through all this data correctly? So if we take the test index and we add... So let me put a breakpoint here. So let's go down to what the original test looks like. So like way down here, we've written all the code again in it. So the original tests, this is like our input data, and this is the input data for the first test, input data for the second test, and et cetera, et cetera. And then we have these are the expected outputs for each test. So this is the first test expected outputs, the second test expected outputs, etc., right? And so what we're trying to do is these three values actually correspond to like values like this, right? We're trying to work backwards, right? So making these binary values is very tedious. So I thought, hey, you know, how about we start with the expected outputs, and we work backwards to create the inputs, and then we plug the inputs into the function, and then check to see that we got the expected outputs, right? So we're trying to like write this kind of test code over again, but where we do everything in reverse almost. So we know that these blocks are blocks of 24, right? So 8 times 3, 24, 8, 8, 16, 24. So we know they're blocks of 24. And if that's true, what does that tell me about looping through here, right? So we loop through every single test, and then this gets us the block index. So the block index should be modulus 24, right? Because 0 is 0 modulus 24 is 0. And when we go 0 to 23, right? 0 to 23, then on the next one. So this base index here should be so if we do, so if I2 modulus, so if 0 is not equal to this I2 modulus 24, then we want an error, and we just want to say a block base so we want to make sure that we have this value right? So if we've made a mistake with how we're calculating this, then it's not going to be evenly divisible by 24, right? Because each block is each block of data for each test case input is a block of 24 values. 3 columns for 3 layers. Each column being 8 values high, because we have tile exponents 0 to 7, right? So we want just a little sanity check here, and we can make, my grandpa is arguing politics with my grandma again, it sounds like. So we want to make a note of this. So the video ID right now is 102, and the time is 1 hour, 16 minutes, and we'll say 42 seconds, or 50 seconds. How about 50 seconds? Okay. Okay, so we had a little sanity check there. And what's the next thing we can do, right? So I'd really like to be able to look at a table that actually represents the data I'm looking at right now, so that I can, as I'm coding this, I can kind of understand what's going on. But we have a table of a whole bunch of values like this. So this is one cluster for the first test, right? And then we get another cluster for the second test, etc. Okay. And let's see where this I2 is being used. So I2 plus the exponent times 3. Oh, you know what? Exponent times 3. Yeah, because the exponent is like the y-axis, right? And 3 is the stride, because there's 3 on here, right? So we're trying to isolate one of these, right? So that's why we have the multiplication by 3, plus the layer, because layer 0, layer 1, layer 2. So if we're on the first test case here, and everything's 0, right? The tile exponent is 0, and the layer is 0, then we just end up here. Now if the layer is 1, then 0 plus 1, we end up here. Now if the layer is 0, but the exponent is 1, then we have to take exponent times 3, 1 times 3, so here, plus 1, 2, and 3, and we end up 1 down. So this makes sense. So what would also help is to have an offset here. Like, we have this hard-coded here, but we know that that means that it's an offset somewhere into this block, and that offset into the block cannot be more than 23, right? So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. I can't exceed 23. So let's say O23 equals, and we'll take this offset here, right? And we'll do O23, right? And then from there, we can say, we could also indent it like this if we wanted to, so that we could kind of see, I don't know. But now we can kind of assert that O23 is greater than or equal to 1, and or actually greater than or equal to 0, and O23 is less than or equal to 23, right? So we can have an assert for that offset there, right? So let's make a note of that. So, you know, at vid IID and 102, and the time is 1 hour, 20 minutes, and 30 seconds. And we'll say, you know, added O23 offset variable plus assert, right? So we have a little note of what we just did here in this section. And we also have to create, like, a variable for that, right? So we got to go up here and be like, okay, where are we declaring all our variables? And, so these are indexes. Technically, this is an offset, so, relative offsets. And this, like, may be way too granular in terms of, like, how many categories I'm making here. So, oh well. So, int 23023, offset between 0 to 23, right? So that's what that is. Okay, so we're going through the tile exponent, we're going through the layers. The tile exponent is 0 to 7, the layer is 0 to 2, right? So there's 8 tile exponents, there's 3 different kinds of layers. Okay. So this is stepping into the actual output data. This I3 is stepping into this block of data here, so that we can target where we want to put the data, right? But then we still need to figure out what the correct binary value, the correct 2-bit binary value to inject into there is, right? So, let's see. So this U16 dex, get index of hextet. Okay, get the index of the hextet. So these are the hextets, right? So we want to look at one of these, right? We want to look at one of these that goes to the appropriate column, right? So we want to figure out what column we're on. And to get the correct column, this I1 is the test index, right? So the test index, Okay, yeah, so the test index, so this is the first test index, this is the second test index, this is the third test index. And we're taking the test index and we're multiplying by 3, right? So if we're here, if we, this is the base address of the first test set of test values, the base address of the second test values, etc., etc. And then we add the layer, right? So layer 0, 1, or 2. Oop, oh god. Layer 0, 1, or 2, right? So we get the index of which one of these things we're looking at, right? And then once we have that index, we need to assert that, so why do we have an assert that we're less than or equal to 39 minus 1? So that is a little bit mind-boggling. 39 minus 1 because we have 39 values that are valid, right? Yeah, 39 because we have 3 times 13, right? And that's 39. Okay, so that's why we have this 39 here. That's fine. And so then this U16 variable is going to come from this table, output table, right? So this is the output table here. We're going to use that index. We're going to get the U16 variable. Okay, awesome. So now once we have that U16 variable, we want to extract the binary from it. And so we're taking this and we're shifting by the tile exponent. And there we go. Found the mistake. Found the mistake. Awesome. So we're shifting by the tile exponent, but the tile exponent is a 2-bit value, right? We're trying to shift out the appropriate 2-bit value, right, and mask it with a 2-bit value. But we see here, we're just shifting it over by the exponent, right? But we actually want to multiply that. So let's make a note of that, right? So so we're on video 102. The time is 1 hour, 25 minutes, or let's say 26 minutes, 0 seconds. Fixing bug. And we can say this is wrong. So the correct... Okay. Sorry, I can't talk. Okay, sorry. I'm gonna change my elastic on my pants here. Okay, there we go. Okay, yeah. Okay, so yeah, this needs to be fixed right here, right? So this is the problem. That when we're trying to shift out this, we're shifting in the correct direction, right? Because the lower tile exponents, like I said, the lower tile exponents are in the least significant bit positions, and the higher and higher tile exponents are in the most significant bit positions. So this is proper. However, we need to multiply by 2, right? So when we see that we want to assert that this value is less than or equal to 3, well, that's not really going to do much for us because we have a mask here. But if the mask was wrong, then that would help catch some mistakes, right? So we're running out of room. We're in these really confined quarters where everything is like ridiculously, you know, smashed in here like this. So let's just take this and just change this to tile exponent times 2. And then think about what we've just done and make absolutely sure that, you know, we're just not being stupid, but I'm pretty sure that that makes sense, right? Because, right, what we have here is we have a 16-bit value. So here's our 8 bits and our 16 bits. And we want to shift it over by 2 every single time, because here's tile exponent 7, here's tile exponent 8, oh, sorry, 6, tile exponent 5, tile exponent 4, tile exponent 3, 2, 1, and then we also have a tile exponent 0, right? So that is why we need to shift over by that much, right? So we can make a little diagram here of what's going on there for reference, right? So this is, you know, tile exponent, 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 right? So this is TE, right? So that's what's going on. That's why we need this multiplication by 2. Okay, so we found one grievous error in this unpacking code. Is that the only mistake we made? Are we out of the woods? We should probably read through the code and see if there's anything else that we did that's completely stupid. So this I3 was... This I3 was an index into not this block, but was an index into kind of a block like this. Okay. And so we're taking the index, so this is the destination, right? Because we're going from the output to the input. So the input is the destination, right? Because we're working backwards from the output table to the input table. And so so UTC in takes the I3, and then that means that UTC out, or how are we calculating out, right? So this U08 var is from here, this is from here, and here's, okay, so this here, we're going to give this a different color here. Right, so UTC, so U16 dex is getting the value that we want to take bits out of, right? And then once we've unpacked bits from this U16 thing, so U16 var, right? Get this UA var. So I'm just saying that, you know, so the output calculations are in orange right now, and the input calculations are in the cyan, right? And I am purposely doing that so that I can kind of see that, you know, we have two parallel calculations going on in here. Well, not parallel in the sense that they execute at the exact same time, but that, you know, logically we have these two parallel calculations that's going on at once, right? Because we're trying to calculate the input index, and we're trying to calculate the output index, and we're trying to pipe the data from the output table into the input table, right? So by color coding this, it just helps me kind of focus on what I need to look at here. Now, why do we have these colors here, right? So what is this? Oh, because this is the output table. So from the output table, we derived a 2-bit value. And now the question is, why the heck am I using a... I mean, yes, it's only a 2-bit value, so yes, an 8-bit variable is enough room for that, but why the heck did I do that? Because tab UC2C in is it really 8-bit values? Is it a table of 8-bit values? Is it? Because I don't know if that's true. So let me put a breakpoint here and make absolutely sure. Is that what? So no. Well, this is U32. So it could be pointing to the big endian table or the little endian table. And this is U16. Yeah, what the heck? yeah, this says U16 here. So it's like, why did I do that? Because that doesn't make any sense here. Yeah, this is uint32 right here. So really, we don't want to be doing weird... Like, I get that, yeah, this is, all these values are really only 2-bit values. We don't need it to be uint32, but we're being kind of lazy with, the way we're doing this, and that could create... that'll create horrible problems for us, right? So if we're pointing to this input table and this output table, right? We're saying U16, but if we're using U32 in other places, and we're mix matching that incorrectly, we're just asking for some horrible trouble. So if we look here, we see, you know, we used U16 here, because there's 16-bit values. And then for these blocks here, I don't know what we use. What do we use? Do we use, yeah, I'm just all over the place here. uint32? Yeah, that's pretty wasteful, right? To make this a uint30, to hardcode this as a uint32. I don't want to rock the boat too much, right? So that, because we're not exceeding the, we're not doing anything where we're going to overflow out of bounds, but yeah, I wish I hadn't gotten so lazy with the way I did that, because I don't want any mistakes from, like, implicit type conversions, because this can be really hard to hunt down. So, that sucks. So, I think that, alright, so, the time is 35, and let's say 50. Yeah, so, yeah, I got a little bit inconsistent here. I'm not quite happy with it, but we're just going to have to hope that... I don't think it's going to cause any horrible problems. I think that it'll work fine. But, you know, putting an 8-bit variable into a table that's either a 16-bit or a 32-bit table, that makes me a little bit uncomfortable. It shouldn't create any problems, but it makes me pretty uncomfortable. But yeah, okay, so then we have some sanity checks here, right? So this is our sanity check section that that we're hoping to pass. And right, so this sanity check section passed earlier because it's just looking at it's looking at these columns, right? It's just making sure that we found the right columns, right? And then, but the thing we got wrong wasn't the U16 variable. The thing we got wrong was that we were unpacking the binary from that U16 incorrectly because we never multiplied by 2 here. And that's why this sanity check passed, but we ended up with the wrong binary values. So I'm about ready to give this another run and see if maybe, if we're lucky, all of the tests just magically pass and we're done with this, and then it's just over. So let's see what happens here. And then I gotta rethink how I'm doing this. Like, maybe I should, like, write enough shader code to get, like, something visually up on the screen, and then write more tests, because this is just... Because my tests are getting kind of out of hand, right? Like, so, outside of... I'm honestly not sure what that did. That looked like a seg fault to me. Because I didn't see any message. So if it's a seg fault, we have to check for like out of bounds access, right? Okay, and that time it just worked. That doesn't seem right. I'm gonna suspend my hotkeys because I'm not sure what's happening here. It's like it's running and then it's just like crashing. Now we're gonna assume that it is my test code that is making something horrible happen, like maybe we're stomping memory or something, I don't know. Right, so this runs. So before enter, this thing begin, end. So let's see what this thing is. Is this like, is this the, test that we're currently in? Do we, like, successfully get through that? But then, yeah, so it looks like we successfully got through all of those tests, and it looks like they all passed. But then... Hey man, been watching you for an hour or two while coding for uni stuff. Just letting you know I'm off to sleep now, but thanks for the stream. Hopefully, when these deadlines are over, I will be able to be more active in chat. Yeah, no problem. And also this stuff kind of just sucks, honestly. But when I get tech demos... Yeah. So right now, this stuff just kind of sucks. So, like, don't even worry, don't sweat it, you know, like, a lot of this stuff is just gonna be boring anyways. But, like, when I get interesting stuff, I'll be sure to message you, right? Like, when I actually get to a point where things start to get interesting... And most things won't be interesting, right? But, like, every once in a while, as I get new tech, I'll have more interesting things to show you. But right now, it's just one of those tedious kind of days where it's just... Most days are going to be tedious, right? Where it's just, like, find the bugs, write more test code, find the bugs, write more test code, right? But I'm glad you watched. I was wondering who was watching, because I'm like, usually I'm just talking to myself. But yeah, good luck with the university and all that stuff, and I will see you when I see you. Okay, so I'm thinking that something about this test is... I think it's doing something weird with the memory, right? Like, I don't remember having any mallocs or anything, so that's kind of weird. But the first thing we could do is we could take this function here, right? This new function that we wrote that's doing, you know, batshit crazy stuff, and we can comment it out, because we're thinking that this test is passing, but then it's, we think that this test is passing, but we're doing something bad with our memory and causing some type of undefined behavior that's causing the system to crash. That is my guess. And that's some horrible, horrible stuff. That's why I wanted to keep all of my sub-libraries small, so that when I accidentally did some type of undefined behavior, we could find it easily. And so I'm kind of scared because this sub-library is getting gigantic. And oh boy, this is just not good. So something else is going on, huh? So let's go between different editors. So we're going between two different editors, that's fine. But then when we go over here, we get the magenta screen for a little bit. Okay, so we're getting kind of like this inconsistent crashing, right? That's not good at all. That definitely is a sign of undefined behavior, like introducing some type of undefined behavior. And oh boy, so we got to think about, like, how are we going to figure this out? Like, how are we going to figure out what we're doing wrong? Part of me says, well, we should. I really want to figure out, like, well, how do we make this PAINT5D kind of thing smaller, right? Like, maybe we need to break it up into, like, 2 pieces somehow. I don't know, but something's going wrong. Something is definitely horribly wrong here. Right, so there we go. We got that again. So the last message we see is this, like, outside of UTC private. Let's put this back in here. So we know that this isn't really doing it. It's actually something else. And the system data restore could definitely be something that causes problems, right? Because we got, like, mallocs and free in there. So that's a contender. So let's make a little note here. Let's log this right here, PAINT5D system data restore, and then when we exit, let's also make a note of that, right? So we're thinking we are doing something horrible, right? Because we're trying not to use mallocs and frees in places. So one of the places where we could really be screwing this up is here, right? So that's my guess. I'm just guessing right now, and that makes me really uncomfortable, but unfortunately, uncertainty is just something we cannot avoid in code as much as we try. So let's see what we get here. Let's see if we can find okay, so that didn't crash, so we're gonna just have to keep on running this until we can get it to crash again and see what the last message we see is, right? So lazily invoke the tests. Oh boy, is it going to be one of those things where we add a log message and then the log message somehow makes everything work? Sure what it's looking like, right? Yep, so that's what it's looking like. It's looking like, that also makes me think that it is something with the system data restore. Right, because this is kind of like the most volatile thing we could probably be doing. So I'm saying that if we comment this out, I bet that the execution path will change and something about this will crash before we ever see this end here. So that is my guess. Undefined behavior is a pain, so okay, so that sucks. We need to think about, well, how are we going to... Should probably learn to use some vel grind here. Okay, so it happened, system data restore begin, end. That seemed to be okay. And then it crashed somewhere else somehow, huh? Yeah, boy. Okay, that sucks. So the first thing is that we're fairly confident that it is the PAINT5D system that's doing something weird. So what we could do is we could try to break things apart. So when we're incurring undefined behavior, one of the ways we wanted to solve that was if we look at our project, we have this thing called a library chain, right? And we decided we were going to break everything down into a whole bunch of pieces so that whenever we incurred some type of undefined behavior like this, and we found things were crashing, we could compile up to a different number and see if things were still crashing, right? So we're fairly certain that PAINT5D is doing it, right? But unfortunately, there's a lot of stuff in PAINT5D, so we need to somehow start to chop down PAINT5D into more smaller pieces to kind of figure out, well, what could be happening, right? So if we change this 26 to 25, right, and we recompile, then we won't be compiling any of the PAINT5D system, right? And if we're not compiling any of the PAINT5D system, then my guess is we won't see that mysterious crash, right? We're just gonna see, like, everything is just gonna work, right? Because it's something about the PAINT5D system. Now, recently we added code for the shader code. So what I'm thinking is that we really need to separate the PAINT5D. We really should separate the PAINT5D shader code stuff from the PAINT5D CPU code stuff, I think that right now we have... Right now, this PAINT5D thing, like, look how big this is. This is thousands, like 10,000 lines. We need to split this up into more than one thing here. Because, you know, something's going wrong. And we think it's in the new code we wrote. But if we could isolate this into another sub-library, we could start to hone in on the problem, right? Because the problem is that when we use this libchan to subdivide our search space to figure out where things are going wrong, indeed, we found the problem is definitely with PAINT5D, right? So PAINT5D is triggering some undefined behavior, right? So we could verify that. We could kind of hackishly verify that by keep on trying to compile this. And as long as we're not including PAINT5D, I pretty much guarantee that we're not going to have any type of mistakes, right? It's just, things are just going to work, right? So, right? So, and we could do this, let's do this like 10 times, right? Let's just do it 10 times to make sure that we have, I don't know if we want to do it 10 times, right? Sure, why not? So yeah, fairly certain that 1, 2, let's do 3, 4, 5. Let's do it 5 times. So we're just going to compile this 5 times. And we're going to assume nothing's going to happen, right? We're checking for undefined behavior really hackishly. Let's do this 2 more times. Still working. Yeah, so I mean, we know that all of our code is probably okay up to this point. But then we have... anywhere we've introduced a malloc or a free, we'll have to look at, because that's usually where things blow up in my face. But yeah, so this works, right? And so the problem is, if you go into our library chain, right, here's all of our systems we're compiling, and we decided not to compile this system, right? We decided only to compile up to system number 25. If we compile up to system number 26, and we try to run the project, you know, 5 times in a row, it's probably going to crash before that. So we add the PAINT5D system, and we go over to, we lazily invoke the test for the PAINT5D system, boom, crashes, right? So we know that the mistake is in this last subsystem, right? So the idea is that whenever we incur some kind of weird undefined behavior from doing something really stupid, that we can have a way to subdivide the project and compile at different steps to see, to kind of do a binary search to the project and see where things are going wrong, right? So I believe we were able to get this to sometimes not crash. It's pretty consistent, but I did see a few times where we were able to get this running and not have it crash, right? So that's why I say that there's probably some type of undefined behavior, right? So like, okay, it didn't crash this time? Yeah, so it didn't crash this time. Okay. So it seems to me that it's some type of undefined behavior, and it seems to me that it's the test code that is doing it. That's what I'm kind of seeing here. So what I think we should do is, I think that this PAINT5D system is getting way out of hand. I think we should make a namespace for the PAINT5D GPU code, right? Because right now we have all of the CPU side and the code and the GPU side code are all like in the same file. And so we just have like a huge amount of stuff, and we have like 2 different unit test sections. We got a lot of stuff in here. And I'm fairly certain that it's actually the unit test code that's doing some type of undefined behavior. And we can actually check that out really quick. Like if we want to verify that, or if we want to be fairly certain that that's the problem, I'm pretty sure it's not the original unit test code, but it's the second set of unit test code. And so this right here, this unit test code right here, I'm pretty sure it's this code here that's doing it. So the PAINT5D OGL, so the OpenGL PAINT5D code, I'm pretty sure it's actually the unit test code that is causing the system to crash. That's just a guess, though. So let's just comment that out, and let's see if we can get the system to run properly if we comment out that kind of unit test code, right? So, all right, no problems, right? Let's do it a few more times, because sometimes it can be unpredictable, right? It's undefined behavior we're doing, so... Alright. So yeah, it looks to me that we're invoking some type of undefined behavior. Yeah, okay, cool. So yeah, we know that it's in here, right? And it's the OGL stuff. So what we should do is we should create a... Can we indent this like that? We should create a namespace called P5D OGL, right? So PAINT5D OpenGL, and it's just the OpenGL side code for the PAINT5D system, right? And that is kind of weird to do that, but I think that the system code just needs to be... There's just way too much stuff in this file, right? So when something goes wrong and we isolate it to this file, we have a problem because there's so much stuff in this file, right? Now, if we could break this into other pieces, then we could have less stuff in this file, and it could kind of help us a bit. So, so I'm saying that we're still going to keep the unit test code in the same file, right? We're going to keep the unit test code in the bottom of the file. But when we're doing Yeah, I think that's what I want to do. I'm going to think about it. I'm going to stop the stream, and then I'm going to think about it. But I think that's how I want to do it. I also need to do push-ups and stuff. So if we look at push-ups, today is 0. It's Friday. I need to get at least 100 done before midnight. And I need to... It's food time. Food time is 9, so I need to do that as well. So I'm going to stop the stream, and then I'll try to get all of my exercise before I start up the next stream. So I will be back later.